Okay, so they will just be, they should see the speaker camera, the speaker which is here, and they'll see that too.
Right, and then this will be this is, oh wait, we just need to put back to the top point.
Alright.
And then
We'll be trying to make sure that the speakers and not the wave function do not get up too far.
Okay, so just use this keyboard to advance the. Oh wait, but you click. Look, so now what do we do? You click the desktop button. Yeah. Okay, there we go. All right. Okay. Thank you. Have it all. Recordings going. Beautiful. Okay. Awesome. Just in time for coffee.
You're thinking it's kind of like this also great. That's the vibe.
I feel like Keith Emerson, I don't know if you're a or like close 70s era, like the grounds of
CLP.
Yeah. So I need to like look at my computer, but advance on both of them. So it's not.
Let me just think. We'll check your rhythm.
There's a chance.
Okay. I see this is the YM
There's a lot going on.
and theme of the conference. Good.
It's kind of like the way Louis just said.
All right, Chris.
See you again. Really well. My oldest was like 5 when she was here. She's in high school.
Yeah.
Great.
About 13.
Well, I would say,
most
basic. I would say, I'm just about to start the next. I don't know when we're gonna have to set down yet.
Composite object.
Right. Relation, but just saying, there's a grounding. That grounding sort of like. Basically because the fact that it always, you do get a big thing if you have some little. Because in fact, true, it's kind of across all little space.
Yeah.
Yeah. Then I would say that's kind of metaphysical causation.
Anyway, guys, never.
It will be a thing that.
But I wanted to kind of. Grounding fact is bringing in.
Yeah.
So I did all that. I think I'm behind you. No, purity fits in. But I wasn't.
Every message.
I was thinking with the story, the much more. Rather than really aren't saying you at all. In the fundamentals. You're just saying. You're, oh no, I thought for a second you were chair next session. The way I get to the end of the covering on it. He's the chair of the So we're talking about where sustenance of claims like the big thing exists because of summer theory or summer
And because I like where you know, if you have the kind of you it's very good.
You mean you plus the big thing on the building.
No, I want to
relation.
Okay.
Other than that,
I know it matters for your you're actually, but sometimes I think
Reality is just not divided. And then you get these surrounding relationships that are.
Oh, yeah.
You've done all the gathering stage, or do you?
I've done all the gathering stage.
You guys still have the distinction between the fundamental. and the-
But
Okay.
I feel like one more gathering.
Yeah, but then you don't think to add on the fundamentals.
That picture,
Time warning. Otherwise, I might, the microphone is just like at time, I'll just wander around.
I will just.
Are you just gonna- Not right here.
No, I know.
I'm not sure, I think we're asking. Some of these questions are more about like higher order.
What does it mean to be on time? How many minutes do I get?
Why, what is why?
40. Okay, I guess.
Yeah, I don't know why. Yeah, I think. Yeah.
Welcome back. We're just gonna start and those lingering in the hallway will eventually get the message. I'll just.
You hereby declare.
Welcome back. We are going to run that. We're about 10, or by now about 15 minutes behind schedule. We're gonna end about 10 or 15 minutes later than scheduled, but then we have a nice big coffee break after that, so we'll sort of catch up with our schedule after that. We have Alison Fernandez chairing, so Alison, I'll kick it off to you to introduce our speaker.
Yeah, so continuing on the theme, we have Sean Carroll, Do Civilizations Rise and Fall in Empty Space, or Why I, Sean, am confused about stationary quantum states.
Thank you very much. Yes, I don't know the answer to the actual title. I gave the title to the organizers with the hope that it would inspire me to be able to answer the question, but that failed. So I gave it the subtitle, following David's good example, and also like to give the impression that after a very long and fruitful career, Barry's real contribution is having a lot of people be confused about it. Which is fine. Like you could definitely do worse than that. Barry, of course, I got to know him around the time that I came out with my first trade book from Eternity to Here, which was about the arrow of time and entropy and things like that. And Barry was very supportive and very helpful. Also very happy to point out the mistakes that I made and where I was saying things unclearly and things like that. Lots of people are happy to point out the mistakes that I make. I should say that. But when Barry does it, it's actually constructive and helpful, and I really enjoy it. So that's why it's such a great pleasure to be here. Why don't I know the answer to this question that many people probably think they know the answer to? I'm someone who believes that the quantum state describes the entire universe. In other words, there's no hidden variables or anything like that. Bohmians don't have the problems that I'm going to talk about. They have their own problems, but not this one. And this is a subtle one. It's a little bit different than what we usually talk about. So consider a spin all by itself, pointing in the z direction. You prepared it somehow, so you know that this is true. You know that I could write it as a superposition of spins pointing in the x direction and the minus x direction. That's just math. So let me ask the philosophy question, what exists? Physicists don't like this question, but you can answer it. And I'm going to give you options, and I'm not going to make you vote, but I think all the options like have some plausible reason to argue for them. I mean, one option is that what exists is a spin in the plus x plus z direction. That's what I said it was. But there's another option that says, well, lots of things exist. There's a single spin, it's pointing in the plus z direction, but there's also two spins. There's a spin pointing in the plus x direction and the minus x direction. And there's an infinite number of other possibilities. And the argument for this case would be, well, were I to observe it, I could make an observation that would either come up with a plus x or minus x, and if I were an Everettian, they would both come true in different worlds. And so if you don't want to believe that I brought them into existence by the measurement, then they were always there in some sense. There's another perspective that would say what exists is the quantum state, don't talk about spins, that's just informal and not very rigorous. And then finally, the physicist answer, which is that what exists isn't interesting or relevant. So I'm happy to be in a philosophy conference where these things are considered to be interesting and relevant. I think they are more than interesting and relevant. I don't know, do we have a consensus? Does everyone, what is the right answer here? No one knows the answer? 3?
What exists is physics.
3.
Uh-huh.
A terrible answer.
It's
Doesn't
interesting
tell
how
me
uninteresting it is.
Anything, okay, I'm gonna claim that you need to answer this for reasons that are kind of related to what David was talking about. We wanna decide, what cosmological scenario we're living in, and to do that, we're gonna try to be Bayesian, so we have different theories, we're gonna update them, by collecting data, like the pattern of temperature anisotropies and the cosmic microwave background, so you presumably want to be able to calculate the likelihood function, the likelihood of getting that data under certain theoretical models of what the universe is doing. At least one way of interpreting that likelihood function is the probability that this data would be collected by an observer somewhere in the universe, like it doesn't matter where you put the universe, as long as that model has that observer observing that data, that counts. But to answer that question, we need to know who the observers are in the wave function. What counts as an observer in the most general case? Sometimes you have a simple case where everything is clear and branched and decoherent and whatever. Sometimes things are gonna be more subtle than that. So we need to be able to count what observers are doing these measurements. And that's a sort of a question for the working physicists, not just for the philosophers. So I'm gonna try to I'm gonna get to these questions by a journey that starts with the arrow of time and, the more comfortable. I've been showing these pictures for a very long time now, so it's a place of happiness for me. Here's Ludwig Boltzmann, who was talking in I put the 1890s, even though Boltzmann started talking about this stuff years before, but in the 1890s. I don't know how many people know the story. He took a trip to England, which was one thing that happened, and he was happy because people in England believed in atoms, and people in Germany, where he was a professor, did not, and he found that very frustrating. But also Zermelo, who was at the time a postdoc working with Max Planck, before he did all the set theory stuff, he wrote a paper using the Poincare recurrence theorem to argue against Boltzmannian statistical mechanics. So Boltzmann started thinking about all these foundational issues in stat mech again. And as far as I can tell, it was the first time in 1897 that Boltzmann wrote a paper where he said essentially, well, there might be a past hypothesis, right? In the 1870s, he was trying to argue that he could use pure physics to show that the second law of thermodynamics must be true. And he sort of by 1897 is admitting that, okay, maybe you need some other thing to make it true. So if you believe the Boltzmannian picture that you can define entropy as the logarithm of the number of microstates that are assembled into a macrostate, then entropy will increase if you start with a low entropy state, just because there are more high entropy states than low entropy ones. So he called it assumption A, and he said assumption A is that the universe started from a very improbable state. That's just the boundary condition he puts there. This is in a very charming paper that is written in English. A lot of Boltzmann papers are only in German. You should read this if you care at all about this, because he's hilarious. He's arguing against Zermelo, and he starts off by saying, like, Zermelo, I was very happy to read Zermelo's objections, because even though they're all very foolish, at least it shows that someone in the German-speaking world is reading my paper. And then he says, of course, I've shown that entropy increases. And he gives 3 different reasons why entropy increases, all of which are entirely incompatible with each other. But he's like, surely one of them is right. And this is one of the scenarios he gives. But then he gives another one, and he kind of hedges his bets. He blames his own postdoc, Schutz. So he wasn't sure whether he wanted credit for this one. He said, look, maybe the universe lasts forever and it's infinitely big, and he didn't know about the Big Bang, so it's eternal and infinite, and he was a little unclear about what gravity would do, but it may be like the stuff in the universe just fluctuates a lot. So he invents both the multiverse and the anthropic principle, as far as I know. He was smart enough to know that if you were in thermal equilibrium, you wouldn't have living beings. So in this vast multiverse where most things are in thermal equilibrium, occasionally, because he's Boltzmann, he knows you would fluctuate downward in entropy and then you would fluctuate back. This is a simulation of entropy in a tiny box of gas. So maybe if you wait long enough, he said, he also didn't know about other galaxies. We thought the Milky Way was the universe, but he says eventually small regions the size of our galaxy will, he's joking here, dry humor, during the relatively short time of eons deviate significantly from thermal equilibrium. He goes on to say maybe we could live there, okay? Completely incompatible with the previous suggestion, but it's another scenario that you might thought was a viable cosmology. And as far as I know, no one followed up on this for another 30 years or so, and it was Eddington who wrote this wonderful book. He coined the term the arrow of time, and he took Boltzmann's suggestion seriously, and he came up with what we now call the Boltzmann brain problem. He said, basically, the Boltzmann brain problem in its most general form says, you tell me what you want to exist in the universe, what you're willing to wait until it exists. An observer, a solar system, or whatever. And the point is that in this eternally fluctuating universe, most of the time when that thing exists, it'll be surrounded by as a high entropy configuration as you can get, okay? No matter what you're conditionalizing on. So Eddington thought that the important thing that you would want in a universe were mathematical physicists. And he says that, I don't know which screen you look at here, I feel like I'm dancing. A universe containing mathematical physicists will at any time date be in a state of maximum disorganization, which is not inconsistent with the existence of such creature. The probability of a downward fluctuation of entropy, again, if you're Boltzmann or Boltzmannian, you can calculate. It's exponentially suppressed by the size, the magnitude of the fluctuation. So conditionalizing on whatever you want, as long as it's allowed, you're not going to extra fluctuate most of the time. And so he didn't use the phrase Boltzmann brains. That was much, much later, Albrecht and Sorbo 2004. As we'll see, this idea comes up again. This picture is from the New York Times, who, as usual, gets it not exactly correct. This is not Boltzmann's brain. Boltzmann's brain is under the tombstone with the equation on it in Vienna. This is a Boltzmann brain. And the idea would be that if you were truly minimal about what an observer would be, the minimal way to fluctuate entropically into an observer would be just to have a brain that was sort of just there long enough to go, thermal equilibrium, and then it would die. And most observers in this scenario should be like that. Now, you may have heard that this is, there's controversies about what to think about this, and I show this slide only with great trepidation, because I know that people would rather talk about this than what I want to talk about in my talk, but I'm going to do it anyway, just to get it on the table. 3 different attitudes one could take about the idea that there might be cosmological scenarios dominated by Boltzmann brains or other kinds of random fluctuations. One attitude, which is by far the leading one amongst theoretical cosmologists, is to just say, well, those cosmologies are ruled out by the data. We have looked around. If you say that your cosmology predicts I should be a Boltzmann brain, I have looked around, I am not, therefore it is ruled out. I do not think that this is good reasoning. It is the majority reasoning among cosmologists who think about this, because I think that there is a huge opportunity for philosophy to be better or to help the physicists in reasoning anthropically. And I might be wrong in my opinion, but my opinion is that we shouldn't be able to forget what we already know about who we are. That it's not really legit to just imagine we're a randomly chosen observer in the universe. Like the typical anthropic principle game is, like I close my eyes and I forget everything I know about who I am, and I go, what would it be like to be a typical observer? And I open my eyes and I'm surprised. I'm not sure if that's the right game to play. I think that we should be able to conditionalize on being ourselves, and then we can ask, like, being who we think we are, what would we also expect to see in the universe? So I think that we can conditionalize on all of our macroscopically available information. And if you do, if you say, okay, I think this room is real, I believe in all of you folks, I have certain opinions and everything, in this Boltzmann brain scenario, most observers, including people who think they're in a room like this and think there's something outside called the state of New Jersey and so forth, will be random fluctuations. They will randomly fluctuate into existence. And we would predict scientifically that if we were to walk outside, it would look like thermal equilibrium. As a matter of fact, no one makes that prediction. So, but I think that that's why this is not the correct logic of the conclusion. Physicists love to get the right answer for the wrong reasons. So this is an example of that. Another attitude, which kind of gets the opposite conclusion from the same reasoning, that's why I love it, is I don't care if there's a cosmology dominated by Boltzmann fluctuations, that's fine. I'm just not one of them. Because I look around and I see that I'm not one of them. There you go. Okay. So there might be out there in the universe all sorts of other crazy things, but I'm not bothered. I don't think that rules out my cosmology, etc., because I know that I'm not one of them. I have a past that was in the aftermath of a thermodynamically sensible, low entropy initial condition, etc. I think that the problem is, once again, this is helping us to inaccessible God's eye view information about who we are in the universe. It fails to quite appreciate the fact that not just most disembodied brains will be randomly fluctuating into existence, but most rooms like this will be randomly fluctuating into existence. So you can conditionalize on being in a room like this, and most of you will be random fluctuation. And you can say, but I just insist that I'm not one of them. I don't think you have the right to insist on that, because they have lives too, those people who are random fluctuations. How do you know that you're not one of them? Why would you choose a principle of reasoning that would almost always be wrong for the people who are actually using it? So I don't think that works either, but there's an obvious easy way out, which is just to say, I think that theories that predict that I'm a random fluctuations aren't correct. I'm going to work hard to invent better theories where that's not the case. And the way that I state this is to say that these theories are cognitively unstable in the sense that you can't believe that they're true and think that you have good reasons for believing they're true at the same time, because in these theories, all of your opinions about science and reasoning will randomly fluctuate it into your brain. And so you believe your own reasoning is unreliable. That's not a way to get through life. So this is where I come down. Different people have different opinions. One way or the other, for the rest of the talk, I'm going to assume that we don't want to live in this scenario. So we can go back to our story. Why is this relevant? Because data, physics, cosmology. In 1977, Stephen Hawking and Gary Gibbons showed that an empty universe with a positive cosmological constant, a positive vacuum energy, has horizons. They knew that. This is called de Sitter space. De Sitter invented this, one of the first exact solutions to Einstein's equation with a positive cosmological constant. There are horizons around every observer in the sense that if you're this observer and you have a friend who is sufficiently far away, space is expanding so fast that your future light cones do not overlap. There's no way for you and your friend to ever see each other ever again, and there's a very definite place where that happens, which is to you, the horizon. And using very similar math to what Hawking did for black holes earlier in that decade, Gibbons and Hawking showed that these horizons associated with the temperature and entropy and the way to talk about the quantum fields, the state of the quantum fields within that horizon is that they are in a thermal density matrix. Okay, they're in a mixed state, just like any other thermal state in quantum mechanics. There's a density operator, e to the minus the Hamiltonian. There you go. And this was considered academic, but Bob Wald showed in 1984, or at least he gave good arguments for something called the cosmic no-hair theorem. Again, in an analogy with black holes, there's a no-hair theorem for black holes. You make a black hole out of a lumpy configuration of matter, all of the individual higher order multipole moments constraining that lumpiness will be radiated away in gravitational radiation. The black hole will settle down into a unique state specified by mass, charge, and spin. The universe does the same thing if it has a positive cosmological constant. As long as it lives long enough not to recollapse, eventually, this is time running left to right. We have an early universe, a microwave background. Here we are with galaxies. Those galaxies are going to fall into black holes. Those black holes are going to radiate away. You'll be left with nothing but cold, empty, desolate space for eternity years. Sorry, but we'll be dead by then. Don't worry. But the thing is that all the perturbations, all the specificity of the universe evaporates away. Our future in this kind of cosmology would be a patch with a horizon around it with a certain entropy and temperature. And then, of course, the astronomers came along, as you know, in 1998 and say, well, we have a positive cosmological constant, or at least what the astronomers actually say is the universe is accelerating. The expansion rate of the universe, the scale factor of the universe is accelerating. The easiest explanation for that is a positive cosmological constant. There's been recent kind of weak evidence that maybe that's not true. Maybe it's not really a cosmological constant, but honestly, we don't know. It's still the simplest explanation. Therefore, put it all together. So we have a theorem that says if we have a positive cosmological constant, we will become de Sitter space. We have a result from Gibbons and Hawking that says de Sitter space has a temperature. We have a worry from Boltzmann and Eddington that if you live in a box of gas with a constant temperature for eternity years, you should be a Boltzmann brain or a fluctuation. So it was Dyson, Club, and Susskind, followed by Albrecht and Sorbo, who coined the term Boltzmann brain, that pointed out that this problem that was kind of an amusing sideshow for Eddington is actually characteristic of our best fit cosmology. Okay, so this is a real world problem. The temperature of our de Sitter phase, which we're nowhere close to yet, we still live in a hot, exciting, complicated universe, but eventually we will cool off to 10 to the minus 30 Kelvin, which is very cold, but it's not zero. So there's a probability of a random thermal fluctuation popping up. And again, you have eternity years to let it happen. So there will be many, many more observers in the history of the universe who will randomly fluctuate into existence in the future than there are people that we think of in the universe right now. And I think that a lot of people still kind of worry about this. So, in fact, Kim Boddy, who was a graduate student of mine at the time, she and I wrote a paper saying, it's possible that certain features of the potential energy function of the Higgs boson could create a cosmological phase transition that would escape from the menace of the Boltzmann brains. And when we submitted for publication, instead of like looking at our calculations, the referee report is like, I don't believe this Boltzmann brain stuff. So we said, okay, we'll write another paper saying you should believe this Boltzmann brain stuff. And we ended up writing a paper saying, actually, never mind, you don't have to believe this Boltzmann brain stuff because you have to believe what the science tells you. What we pointed out was that there is kind of a linguistic fooling of ourselves that is going on when we talk about the thermal density matrix of de Sitter space in our future cosmology. Classically, if I have a box of gas that I say is at thermal equilibrium, maximum entropy with a certain temperature, the classical distribution function is stationary, right? It's the Maxwell-Boltzmann distribution. It doesn't change over time. But that's kind of an epistemic statement. We think that really there's a bunch of molecules in there, atoms and molecules moving around with essentially, from our point of view, random motions. So even though the Maxwell-Boltzmann distribution is static, we believe there will be fluctuations downward in entropy, like we said in the plot of the simulation. Quantum mechanics is different than that. If you're someone who believes that the quantum state is the whole thing, if you don't believe in hidden variables or whatever, in quantum mechanics, a thermal state is the complete description of the system. It's not forgetting anything. It's not epistemic. Here it is. And there's no T for time in here. It's a completely stationary quantum state. It's tempting to look at a thermal state in quantum mechanics and go, oh, there's little thermal fluctuations in there. But if it's the whole universe, that's not true. It's just sitting there. It is true that were I to perform measurements on this density operator again and again, I would get a set of fluctuations, right? I would get a probability of getting different measurement outcomes, but there is nobody performing any observation. This is the entire universe. It is exactly the same from moment to moment. So we argued that in fact, there will not be observers fluctuating into existence in this kind of quantum state. You were tricked into thinking there were by thinking about classical mechanics, but the actual quantum state is just going to sit there. It's not going to change from moment to moment.
Couldn't that quantum state, the very same one, be written as a mixture of wave functions which are changing?
You can write it in a mixture of all sorts of things. It is not changing though.
In itself, but if that's just really just the usual kind of genuine mixture,
You remember I started my first slide asking this question about what we should consider to be real in the superposition.
that was for the wave function.
Sure, it's the same exact question.
Okay, you want to elevate the wave function, now it gets replaced by the density measure.
As it should for this particular physical situation, yes, but I think the
That's how it's
questions
generally
being
regarded,
asked are the
okay.
same, yeah. You can absolutely think of this wave function as reflecting the fact that the universe, the whole de Sitter universe is in a pure quantum state, but you're only looking at a subset.
Mhm.
So that pure quantum state is stationary. Okay, so we argued that there were two possible scenarios that were relevant, depending on, interestingly, the dimensionality of Hilbert space of the universe. Something that I never thought would really, I used to be, when I was young, I used to think that 10 to the 10 to the 120 equaled infinity. Apparently it doesn't. Apparently those numbers are different. So one possibility is that the entire universe is described by a finite dimensional Hilbert space. And we even know what it is. It's of order e to the 10 to the 122, okay? And I know that you might not want that to be true. You might have been taught that even the simple harmonic oscillator has an infinite dimensional Hilbert space. I think we should be open-minded rather than choosing ahead of time, because we don't know a lot about the quantum mechanics of the universe as a whole. So this is on the table, except when you have a finite dimensional Hilbert space, there is a recurrence theorem. There's the quantum version of the classical Poincare recurrence theorem. And indeed, the universe, this universe, if it's changing with time ever, then it's going to change with time forever. It's never going to settle down. It will always be evolving in Hilbert space. It will spend most of its time in some coarse grained state that looks thermal and approximately stationary, but there will be fluctuations downward in entropy. You will have the Boltzmann brane problem, and I would argue that you should not allow that into your list of viable cosmologies. The other possibility is that the world, the universe, the theory of everything, has an infinite dimensional Hilbert space. This is a space-time diagram, Penrose diagram for de Sitter space. So time goes up, space goes this way. We live inside this red triangle here. And the cosmic no-hair theorem says that as time goes on, all the excitations of our universe, all the galaxies, etc., leave our horizon, and we live in a vacuum state. And if the whole universe has an infinite dimensional Hilbert space, then that continues forever, and you just asymptote to that static quantum state, that static density matrix. In this case, we said there are no fluctuations, there are no Boltzmann branes, so you can escape the prediction of the Boltzmann brane worry, even in your favorite cosmological model, just by imagining that the theory of everything has an infinite dimensional Hilbert space, which maybe you thought anyway, so you should be happy with this. And people argue about that. So one person who argued about it was Seth Lloyd, who was a quantum information guy at MIT. And he said, wait a minute, I think lots of things happen in static quantum states, whether or not you want to call them wave functions or density matrices. And his argument was based on the decoherent histories of formalism. Decoherent histories formalism is one of these wonderful things that is like too formalistic to be of much use to anybody. It requires a lot of notation and a lot of symbols and things. I'm going to try to get the point across. Decoherent histories formalism says the following thing. It's Everettian in spirit, although for sociological reasons, people who use it don't like to call themselves Everettians. But imagine that I have a quantum state that is evolving in time. Okay, so time goes vertically. And what I do is I choose certain measurements that I don't actually make, but I imagine I could have made. Okay, so I'm not collapsing the wave function. I'm not doing anything that changes. The quantum state is just always obeying the Schrodinger equation. But I'm going to invent a set of projection operators that you can think of as measurements. So I'm going to measure the position of a particle coarse-grained to some, cubic volume or something like that, okay? And I'm going to do measurements, a complete set of measurements at different times. I'm going to ask myself, what could the outcomes of those measurements have been? So by doing that, I make a set of histories. A history in this case is just a list of possible measurement outcomes. At time one, the particle was there, at time two, it was there, at time three, it was there, that's a history. And then the game that you play, the thing that you're supposed to learn by doing this, is you can calculate whether the set of all the histories mutually decoheres. And if it does, you can assign probabilities and say that's like a classical looking world within this wave function. So the example they always give is the double slit experiment. You can think of the projections as saying the particle was at the source, it was either in the left or the right slit, and then it was at various points on the detecting screen. When you don't monitor which slit the particle goes through, you can have you can have many different histories. Some of them go through the left slit and then hit somewhere, some of them go through the right slit, but they don't decohere from each other. They interfere with each other. So the lesson that decoherent histories teaches you that you already knew is that you can't say whether the particle went through the left or right slit, because those histories don't decohere. When you monitor which slit the particle goes through, then they do decohere, and you can assign probabilities to both of the histories, and they say, good, and we knew that. Once you measure which slit the particle went through, you get an answer. There's a probability went through the left, probability went through the right. So there's a big, powerful formalism for doing that. And what Lloyd says is, we can do this with a perfectly stationary quantum state. In fact, he literally looks at the ground state wave function of the simple harmonic oscillator. Okay, I plotted it there, SI naught, and the simple harmonic oscillator, as already mentioned, has an infinite dimensional Hilbert space, which makes things tricky. He says, that's okay, I'm just going to truncate it. I'm just going to look at the first capital N energy eigenstates of the simple harmonic oscillator. This is a little bit more technical than we need, but I'm sure there's some people in the audience who want it. So he invents these phase states, which are kind of like literally thinking about the ball rolling back and forth classically in the harmonic oscillator. He invents projection operators that are adapted to them, and he cleverly hooks it up so that the projection operators just march forward in time to the same set of projection operators, but sort of rotated a little bit. And then he does the math. Here are histories. Do they decohere from each other? Yes, they do. So in the ground state of the harmonic oscillator, there is a set of individually dynamical histories which decohere from each other. You could assign probabilities to them. And then you ask yourself the questions, okay, does that count as happening? Is this thing that I thought was a completely static quantum state sitting there and not changing over time, is it better to think of it as a superposition of many dynamical things all happening? And Lloyd says yes, because he says the criterion is simply, can I find histories that decohere? That is all that I care about. So maybe, maybe not. And these other folks have also pointed out things like this, and they've raised a worry, and no one listens to them. So I think it's kind of interesting. One big worry is that this is a lot of histories, because in his paper, Seth Lloyd, picks out very specific trajectories for these histories that happens, and you might get the impression that, okay, there's a certain weird set of histories that are all happening in the ground state. But in fact, it works just as well for you give me any initial measurement outcome at all of the ground state. And I construct a projection operator that projects onto that measurement outcome, psi star. And I construct another projection operator, which is everything but that. And then I use the Heisenberg equations of motion to evolve them forward in time. And I get another set of histories, and you can easily show they all decohere from each other. There's nothing special about these phase states that Lloyd uses. So if you think about what this means, everything is happening all around us all the time. Because as long as I have, if we thought that the universe was in the Minkowski vacuum state, any possible state that has a non-zero overlap with the Minkowski vacuum, I could project onto, could evolve it forward in time, and I would have to say that is happening right now. in the Minkowski vacuum state. That's the civilizations rising and falling. There's a thing happening in the Minkowski vacuum right now where we're having exactly this conversation, but you are all Everettians. There's another version where David is giving this talk and I'm giving the talk that he just gave. Everything that is happening, there's a non-zero overlap, okay? This can't be right. I'm not here to tell you this is right. I strongly believe this is not right. I also strongly believe that we should not just say it's not right. We should be able to give a principled reason why it's not right. And I'm not quite sure what that principled reason is. I have unprincipled reasons for not liking it. One is that the existence of these fluctuations has nothing to do with the original motivation, which was that we're in a thermal state in de Sitter space. The existence of all these decohering trajectories is just as true for the zero temperature vacuum as it is for a mixed thermal state. The second thing is, as I said, Lloyd gave us some specific, a specific set of decoherent histories, but there's many, many other different sets of decoherent histories. And if you believe that one of them is really happening, you should believe that all of them are happening. And the rules of the game let us assign probabilities to histories within families of history, but they do not let us assign probabilities, or they do not offer us any way to assign probabilities to sets of different histories. So we have no way of saying if there's no sense in which there is something that does happen and something that doesn't happen in this scenario. Finally, it's just weird because you're saying that the state that we're in is just the ground state. And then you're using the rest of the Hamiltonian that is not the ground state to actually construct these histories. And the question becomes, how do you know what the rest of the Hamiltonian is if you're living in a state which is just the zero energy state of the Hamiltonian? So all of these kind of tell me, they're convincing to me that all these don't happen. But I would like to be able to give you like the hard and fast criterion for this is what happens and this is what doesn't. I'm not quite sure I can do that. And it becomes even more relevant when you realize that everyone working in quantum gravity has this problem. Like you might say, well, okay, I live in a non-stationary quantum state, so I don't have this problem. Of course, nothing about the problem needs you to live in a stationary quantum state. It's just there even in the stationary quantum state. But there's an argument from quantum gravity that we live in a stationary quantum state. Here's the Schrodinger equation, but in classical general relativity, at least for a closed universe, we can argue about that, but for a closed universe, the Hamiltonian is a constraint. It is not an equation of motion. It has to vanish identically. And in the quantum version, you get the Wheeler-DeWitt equation, which just says h psi equals 0. There's even a halfway respectable argument that this does not depend on details of general relativity, it just depends on the diffeomorphism invariance of the underlying classical theory you start with. So almost any halfway decent theory of quantum gravity will give you an equation like this. But you notice that time has disappeared from that equation with their usual perspicacity. Physicists have named this the problem of time. Where did it go? That's the problem. And then they will say, don't worry, it's emergent. And everyone says, oh, okay, good. That clears everything up. It's emergent. What does that mean? It's emergent. Well, there is a kind of favorite meaning attached to that. Comes from a paper by Page and Wooters back in 1982. They say the following. Imagine that I have a Hilbert space that I can factorize into a clock and everything else. A clock in the universe, okay? And I have a Hamiltonian that annihilates the state, and there's no interactions in the Hamiltonian between the clock and the rest of the universe. So when I act the Hamiltonian on the state, basically, I get a non-zero answer for the Hamiltonian acting on the clock and a non-zero answer for the universe, but they're minus each other and they cancel out. And then if I happen to be in a nice state which is entangled between clock readings and the rest of the universe, Page and Wooters very cleverly derive that there's an effective Schrodinger equation where you're saying that the rest of the universe evolves with a time parameter which is just the reading on the clock. And that is what it means for time to emerge. It's good enough. Like when you're convinced this is the answer you want, a lot of people are made happy by this. Not everyone is made happy by this. Andy Albrecht points out, You made a choice about factorizing into clock and the rest of the universe. What if I make a different choice? And he shows that I can get any effective Hamiltonian I want. There's no such thing in the setup as what the laws of physics are. That would be bad if you're a working physicist. This paper, and he's followed it up with other papers, and he has a whole website called The Clock Ambiguity, and nobody cared. I asked Juan Maldacena, who just gave a talk about the Wheeler-DeWitt equation. He says, I have no idea. Someone else will solve that. So here, I wish I had solved it. That was my goal. That was my goal with the title of the talk. It didn't work. I did not solve it. So I have a couple more slides just about the aspirations that were unfulfilled. I do have ideas about if I have a Hamiltonian with time in it and the Schrodinger equation, but the Hamiltonian has no extra structure built into it. It's just a spectrum. It's just a list of energy eigenvalues. I think you can argue in a principled way that structure emerges very naturally. There's a paper by Kotler et al., which says that locality can emerge. In other words, I can divide up, if I want to divide up Hilbert space into factors that represent local field theory vibrations in different parts of the universe, that's super constraining. Most Hamiltonians don't let you do that. When you can, it's essentially unique. So if you have a Hamiltonian that lets you have a local understanding, you can find it in principle. And Ashmeet Singh and I did a similar thing with dividing the universe into system and environment, so you can look for a good semi-classical approximation to the world. So what I want to happen, I feel very bad, I'm telling you what I want to happen, I have no idea whether it happens or not. But here would be the glorious thing that if we could make it happen. What if the state of the universe is given by a density matrix? So density matrix realism. I know there are some people who want to do that. Because if I just have h psi equals 0, there's no spectrum of the Hamiltonian to work with. I mean, there is, but it's the number 0. That doesn't really pick out anything. If the universe is described by a stationary density matrix, then at least I have some data. I have some information, the values of the density matrix, right? So this famous thing, you can use that to define the modular Hamiltonian. You can say, well, what would the Hamiltonian have to have been to make that density matrix look thermal? This is a fancy way of saying I could take a logarithm, I could make something that looks like a Hamiltonian, and maybe, I don't know, but maybe that could be used to pick out a factorization of Hilbert space into clock and the rest of the universe. Maybe even, as a consequence, the beginning of time would be low entropy for some nice reason. Maybe you would have a reason from the emergence of time to explain the arrow of time as well as the problem of time. I told you we were aspirational. And the nice things is, because the whole Hilbert space is finite dimensional, there's only a finite number of ticks on the clock of the universe. Time does not last forever. There's no recurrences. You can avoid the Boltzmann brain problems and things like that. In the famous phrase of Wolfgang Pauli, details to be filled in later, but this is the kind of thing we're working on. And I'll just close by saying philosophers have not paid enough attention to this. There's this wonderful article in the SEP about time, and I looked for this issue in there, and there's a little thing that says time in physics, in small letters, and there's one paragraph that asks, could time be emergent? And that's literally what it does. It just asks. There's a whole bunch of rhetorical questions. There's no idea. Like, yeah, maybe. The physicists need help with this. Philosophers need to train their brain on this problem. And I will close by thanking Barry. I think my favorite quote of the many, many quotes you can find from Barry is this one that he said to me. It was a shock when I realized that most problems of philosophy can be solved by thinking about statistical mechanics. Just add quantum mechanics in there. I think it's all the problems of philosophy could be solved. Thank you very much.
Okay, questions, just keep your hand up until I nod. Michael, do you want to say?
This is a question about the whole kind of motivational structure of the talk, because it came across two different ways of thinking about it came across. One was this: I really don't want to be a Boltzmann brain. I really want New Jersey to exist. I'm going to go and see if I can find a reason to believe I'm not a Boltzmann brain.
I confess to all of those terrible thoughts, yes.
And then the other one was more, I'm not a Boltzmann brain. And I will therefore reject any cosmology, any physics that makes it highly likely I'm a Boltzmann brain. And now I'm just going to go and look for that physics, the correct physics, which will allow me to rule out that possibility. So with that one, you kind of, you have this confidence in advance that New Jersey exists, that you're lacking or possibly lacking in the first. And it was in the first part of your talk, it sounded a bit more like the second of those, and the second part of the talk, aspirational, came up and sounded more like the first. And I'm wondering, which is the real you?
This question makes me happy as a scientist because I made a falsifiable prediction and it came out true, that this is the only slide people would want to talk about. No, I do not. I'm not working on any conjecture or claim or assertion that I am not a Boltzmann brain. I might be, but if I am, I'm out of luck. So I'm certainly going to act as if I'm not and proceed accordingly. And maybe the rhetoric doesn't, I mean, maybe I'm acting like that so convincingly that it seemed more solid than that, but that's just, I feel like a lot of things, like in the aftermath of David's talk, you know, I think that one of the things I've made peace with in the world is that a lot of things are a little fuzzy and not deductive, right? I mean, I have to say like, well, I gotta act this way because that's the best I can do.
It sounded like what you approvingly quoted 3 there.
Yes.
That looks like a kind of an argument that I'm not.
But it's a normative argument. It's
So
not,
that's not the.
it's not an argument that
it's
I
not the
am not a
rational
Boltzmann brain. It's an argument that I should act as if I'm not.
I'm so curious too. We can maybe come back to this issue.
I do not have a question about this slide, so, yeah. I have a question about the invocation of Bob Wald's no-hair theorem, the de Sitter no-hair theorem. I don't remember the proof of that theorem. Is that a purely classical theorem? Is it a theorem of classical GR?
As any great scientist does, he wrote the classical paper, then other people wrote the quantum paper and cited him, so.
Is there well, we don't have a theory of quantum gravity, we don't have a
There are
well-defined
QFT and curved space-time versions of the cosmic no-hair theorem.
Right, but doing QFT and curved space-time is not dynamical gravity, right?
No, it's not.
We don't have a theory of quantum gravity, so how seriously should we take the validity of this no-hair theorem in a quantum gravity context, which is presumably what we care about? And if it's not exactly right, and de Sitter universes are huge. So even tiny
Not as big as non-de Sitter universes, what are you talking about?
Yeah. But I just mean that like, they're very big, teeny discrepancies between classical, no-hair theorems about a de Sitter universe and a quantum gravity description are just because the universe is so big, gonna be galaxy size. So I just don't know how to, yes, maybe there's some sense in which this no-hair theorem holds, maybe it holds to some high precision, maybe the discrepancies, that show up with quantum gravity are tiny. But how do I know those discrepancies aren't like galaxy size and big enough to squeeze a whole so I just don't have enough control, I think, of the technical assumptions here to be able to evaluate whether we should be worried that we're asymptoting to a truly stationary state to a level of exactitude that it's smaller than galaxy size, you know what I mean?
Sure. We don't understand quantum gravity, so it's always possible, right? I think that when things are galaxy-sized, quantum field theory and curved space-time has every right to be pretty good, to be honest. But we could be wrong about that. I mean, it would be certainly a fascinating discovery if you could show a counterexample. Also, though, morally, I think the cosmic no-hair theorem should be thought of as the second law of thermodynamics. I wrote a paper with Aidan Chapman Davis where we showed that in a certain controlled set of conditions, entropy increases and then it asymptotes to a constant value and stays there forever is equivalent to the cosmic no-hair theorem. So that's why I think there is a certain robustness about it, even if I don't have a full theory of quantum gravity.
Okay, thanks.
Thank you, Sean, for a great talk. I was glad to see continuous realism getting mentioned in the end of the talk. I remember, talking about many people about the coherence position. That was still, something that people fight for. But in terms of how they become part of the factorization, the quantum meteorology program, I was wondering if you say more about how this might help in the spectrum in terms of the getting modular Hamiltonians. And I was wondering, this kind of a maybe deeper question. It's a worry about quantum meteorology. As you know from the paper with Jim Alkalidi, So we argue that, well, do we really get everything for free? You have to assume space somehow, even formulating the condition of a quantum system, such as the quantum, entanglement path hypothesis. The factorizations is privileged by using spatial intuitions. So conceptually, there's a word about circularity, whether you build in space to get space out. But I was wondering on this picture, or maybe just a general picture of phenomenology, how to avoid this potential circularity?
I think, don't worry, as you age and grow in wisdom, you will overcome your devotion to space and time and just live in Hilbert space. And then it will all seem very natural. The idea here is, there is no, the way that you would phrase the past hypothesis is obviously very different if you don't have some preferred factorization. But like in many, I make fun of emergence, but I think it's true. Like in many cases of emergence, the factorization is not preferred in the sense that it's part of your ontology, but it's absolutely real, as Daniel Dennett taught us. There's the right way to factorize Hilbert space so that it looks like local physics to us. And then I think it's perfectly legitimate to ask what the world looks like in that usual factorization. I do think that there's a lot we don't understand, especially about the dimensionality of Hilbert space, the recurrence and things like that. But this is all, I'm not worried. I don't think I am relying on my intuition. I think I'm relying on equations.
Okay, Mike.
Great. Thanks also for a great talk. I was just wondering if you could, so you presented the problem of time in a decoherent histories framework. And I was just wondering if it looks better if you're willing to add in more. So a long time ago, I talked to Ward Stroiva, and as you might imagine, if you know him, he thought Fovean mechanics had avenues for solving this, because in addition to the quantum state, you've got the distribution of particles, moving around, and that can help you choose a preferred factorization for
Sure.
thoughts. And I wondered if you were an explicit Everettian, if you also had. So
It has been claimed that my Everettianness is worn on its sleeve, yes.
Yeah.
I do not hide that.
Yeah, but either way, it seems like you might have more opportunities for saying which factorization is correct.
So I am like the most hardcore of Everettian. I think that the ontology of the world is a vector in Hilbert space. And the way it evolves is under a Hamiltonian, which is just a list of energy eigenvalues and nothing more at all. And again, I'm happy to be talked out of that because it's like a intentionally extremist position. We're trying to see how far we can go with that. But the answer is like further than you might think and far enough that you're encouraged to keep going and trying. Of course, you can answer a lot of problems by saying, I put the answers into my theory. And we might have to, and I completely agree with that, that we might have to. But if we can get away without doing that, it's better. I think that if I have like a simpler, more austere starting point, I can derive all this stuff, I win.
You've got room if you wanna.
Yeah, I was actually thinking, if you're full-blown Everettian and not just a decoherent histories person who's kind of quiet about the Everettianism, you might have more opportunities to respond to this without invoking the stuff Bovians require. And I was thinking you might just say something like, look, I already think that what counts as a world is dependent on some arbitrary choices of coarse graining. And so this is just amongst those. It's not like a new problem. But you don't think that.
I don't think that, well, I think that it depends on choices that are not arbitrary. I think that there are criteria for making the right choices. This plot, which I didn't describe, sorry, but in our paper, we said, let's imagine we have a simple system and we factorize it into system and environment. And we invented some quantitative criteria for the physics of the system part looking classical. And we looked at a toy model where we knew that it would look classical at a certain factorization. And then we random walked away from that factorization and calculated our thing. And we found that our criteria minimized, gave you the quasi-classical factorization you wanted all along. So I think this is a general thing, that if someone just gives you literally a spectrum of the Hamiltonian, I can sift through all the possible factorizations, apply our criteria and go, there's the classical world.
Great.
Cool. Tim?
Yeah, so, I mean, I have many questions. Let me do three really quickly.
One of these days, you're just gonna say, yeah, all right, you're right.
I don't think time goes on that long.
How about keep trying?
One is real, so I mean, okay, so you go back to Boltzmann, and Boltzmann says, if you give me an initial state that's low entropy, now I have these arguments, you can think of them as typicality arguments, the entropy will increase, it's highly likely to increase, whatever you call it. That would explain what we see around us in the second law, conditional on the initial state being low. What about that? As you say, in the paper, Boltzmann says, well, maybe that's just the fact, right? That's just an additional fact. Initial state was low entropy, or if you're Roger Penrose, you maybe say its wild curvature was 0 or something fancy like that. Okay, that's good. And then, I mean, you say he blamed it on his assistant. He does say his assistant had this idea that the whole thing is in thermal equilibrium and you get these fluctuations down. Now, those fluctuations are real honest to God fluctuations, and I'm not sure why that proposal even still exists. Feynman nicely pointed out, as you know, that theory makes predictions, at least if it makes any predictions at all, it makes bad predictions, right? Feynman says if that were true, if I point my telescope in a direction I never pointed it before, I should not expect to see stars. I always do see stars. Now, if somebody says, no, you just think you ever saw stars in the past, but you fluctuated down with false memories. Now we're in, Cartesian skepticism. We're not doing physics anymore, right? We're just not doing physics at that level. So I don't even know why anybody talks about that. But you did, so that's one question. The second one is, then the word fluctuation gets completely screwed up when you get to quantum mechanics, because people say, oh, there are all these fluctuations in the vacuum state. You say, what the hell do you mean? It's stationary. It ain't fluctuating. Oh, well, I've got the expectation of x squared and the expectation of x squared, and that's a number. It ain't a fluctuation. And then you get these, well, I'm going to have these decoherent histories by pretending someone made a measurement. I mean, the way you described it, I'm going to pretend a measurement was made here and then pretend a later, what the hell? You're now talking about these pretend non-existent measurements and, understanding the world. I don't understand any of that. And then I don't understand any of this. There's a lot of the saying, look, I can find a factorization which has nice feature X. And you can find lots of factorizations that don't have nice feature X. I think the world has nice feature X. You think that your thing explains that? Why don't you say no? What makes, I mean, it's like saying, it's just wishing, right? There are a billion factorizations, like a billion ways to write a vector as a sum of other vectors. And you say, well, if one of them is the one I like, then I win. How about if all of the other ones aren't the ones you like, then you lose? I just don't understand what the methodological principle is here.
I'm happy to help. So you asked why people are talking about Boltzmann's scenario, because people were worried that it was the real world, because our best fit theory of cosmology, our best fit to the data, predicts that the universe will last forever with thermal fluctuations, which is exactly Boltzmann's scenario. So we need to worry about it.
No, it's not. It's not the assistance scenario where it was thermal equilibrium way in the past. That was his scenario. That leads to the problem that Feynman objects to.
Well, so Feynman's problem is exactly the same as Eddington's problem. This, like you say, living in a universe like that raises this hugely devastating skeptical scenario. And
we're not communicating with each other. The problem is we agree, we know right now we're not in a maximal entropy state. Question, why not? Answer one, we fluctuated down to where we are. Answer two, no, it started way low. We never fluctuated down to it. It just started low.
yes,
That was the question. Two was Boltzmann's. One was his assistants. His assistants has been knocked out. It's empirically inadequate. Makes bad predictions.
right. But in our best fit modern cosmology, this claim was that if you just let it evolve forever in time, in the set of all people like us in rooms like this, most of them will be random.
We understand that's a different problem. That wasn't the problem that Boltzmann was addressed.
maybe add a finger on this. I mean, if you've made an explicit posit in your theory, that by the way, we're not too far from the low entropy state or something like that. I take it the proposal is something like, that's what our best theories are like, rather than like ones where all I say is that I have a very long lived universe with these kind of fluctuations in them.
No, so again, I think that you're not allowed to do that. That's this move right there. I'm not gonna let you do that. I've forgotten Tim's other questions. I can probably find them because I have answers to all of them. They're really good. What was the second question? Just some words.
You know, this use of the word fluctuation for the calculation of a certain quantity, which does
Right.
not
No,
imply
I
anything
agree
is
with you.
actually
We
fluctuating.
wrote a paper saying that. Yeah, so that I disagree with you. We're just on the same, you actually do agree with me.
Good.
And then the final one was about these. Yeah, you agree with me there? Good.
I mean, the final one was about why should I take in
Oh, yeah, emergence,
comfort
right.
in the existence of a factorization you like, given
Right.
the existence of almost infinitely other factorizations you don't like.
This
I
is
just don't
exactly
understand the
the same-
methodology here.
It's the same reason why we coarse grain the air molecules in this room to get fluid dynamics rather than in any of the infinite number of other ways we could have done.
We coarse grain it with nice little boxes. If you
Right.
had to coarse grain it with weird boxes, you wouldn't be satisfied.
Right. Good. I'm glad we agree.
No, but I don't understand. What, all you've said is there is a factorization.
Yeah, so we're gonna use the good one.
But good here doesn't mean the one that gives me the result I want.
No, it means the ones that gives me an immersion theory that works on its own terms. That is to say, I can make
You get
predictions
lots
about
of
what
immersion
happens.
theories that work on their own terms that don't look at the universe we see. Out of the same thing.
Well,
I mean, you referred to Dennett there. I mean, you're an expert on the emergent stuff with Dennett. Okay, explain to me what Dennett said that's helpful and true.
the specific kind of emergence that we have is one where you have theories at the higher level that are self-contained and autonomous and based on what looks like wildly incomplete information from the microscopic level. My claim is that the existence of such theories is very rare and precious. And that is precisely what we are looking for. We are looking for coarse graining that give us variables that solve equations all by themselves without any extra input.
All right, I'll just add, so you're translating a factorization equals a theory. In what you just said. You said we have theories that blah, 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 but what you say here is you have factorizations that blah, blah, blah.
Right, of course.
So you're saying a factorization is equivalent to a theory?
No, but you obviously you use a factorization to define your coarse graining that will give you the theory.
All right, I'll stop.
All right, I'm gonna have a go about the slide with the three views that I
All
want
right.
to talk about.
Go ahead. I gotta find it, so.
Sorry. I also got confused by what the question was that was being answered and what the kind of reasons were that are being given here. And I might just say it as I'm thinking about it and then you try and adjust it to here. So one question might be like, are there any Boltzmann brains in my theory? Another might be, am I one of the Boltzmann brains in my theory? Another might be, should I act or believe as if I'm one of the Boltzmann brains? And then in terms of our reasons, you might be giving like cognitive reasons for thinking that's the case, kind of justifying reasons, or you might be explaining why something is the case or not. And I got confused by what these claims actually were. So is this one saying there aren't any Boltzmann brains at all?
These are three different attitudes toward cosmological scenarios with Boltzmann brains.
Yeah, I'm trying to specify exactly what we mean by attitude and what the commitments are of each of these three things. Assuming that attitude towards is being read as a kind of general thing here. Like it's not just one question being asked by the Boltzmann brain scenarios. I might have different kinds of responses.
There are certainly questions within the scenarios. This question is about, I'm a working cosmologist. I have various theories for what could happen in the universe. Some of them have the feature they are dominated by Boltzmann brains, and some do not. What should my attitude as a working cosmologist be toward those theories that are dominated by Boltzmann?
I feel like I'm not getting the precision I want, so I'm gonna try and attack some of this stuff.
Okay.
So I might think that they're cognitively unstable, and I might draw different kind of conclusions from that. Shouldn't be taken seriously, just sounds like I just ignore them or something, like I don't sort of
Yes.
bother theorizing about them whatsoever. Or you might say they're cognitively unstable and I shouldn't adopt a theory that says I'm one of them. That seems really bad. More strongly might be something like they're cognitively unstable, therefore the theory shouldn't have been in them at all, because there's no way to block me being one of them if I have a theory like that to begin with. Or it might be weaker, you know, they're cognitively unstable, therefore I should never adopt such a theory. But I realize I might be in a bad situation where such a theory is nevertheless true. And I'm not sure what attitudes are being recommended or kind of dismissed here by the claim about cognitive instability, which I kind of agree with, by the way. I just always thought that went quite nicely with various empirical claims that said, so we shouldn't adopt a theory that says I'm one of them. And then what's going to explain this is something like closeness to the initial entropy state.
So I read this as saying that as a theorist thinking about cosmological scenarios, your prior on scenarios that are dominated by Boltzmann brains should be essentially zero.
That bit's all okay, and the rest of the questions still follow.
You wanted a specification of this, that's that, it's very precise.
So is the claim so they're appearing anywhere in the theory is going to be bad, or just
Dominated by Boltzmann brains. So if I conditionalize on what I take to be my macroscopically available information, and I say that a certain cosmological theory predicts that most observers subject to that condition will be interpreted as random fluctuations from higher entropy prior conditions, then I should assign essentially zero credence to that scenario.
So there's no way to add something that you might call, I don't want to say it's self-locating, but an indexical proposition, like, by the way, we're near the low entropy potential.
That's this one, and I think that that's not allowed. I think that's cheating. People have tried, people disagree with me. So Carroll and Schridnicki wrote a series of papers where they suggest that a full theory of cosmology that has multiple observers in it includes both the specification of the whole universe and an extra zero graphic distribution over the probability of being different observers within it. But the definition of that uses knowledge that no observer could ever have. And I think that that's not fair.
So I was suggesting, I guess, that the reasons you gave here may actually support, because the just is kind of bad there. I just insist sounds like for no reason. I'm just kind of, whereas this might be a reason.
I don't think we're allowed to do this. So I'm not trying to give a reason to do this.
So we're allowed to do this.
Yes.
But why doesn't this lead over here?
Because this is the statement that most observers are Boltzmann brains. I'm not one of them. This is the statement that in my cosmology, there are almost no Boltzmann brains. Those are two different statements.
So there's also statements here about reasons.
Yes.
So I'm using the reason for here. I'm going to stop in a minute because I don't feel that would help me.
I'm missing. We'll
But
talk later.
like, happy to.
I'm missing something. Yes, sorry.
All right, Eddie.
So I asked another question about this slide. I was wondering about the third option, the one that you prefer in the end, which is to try to avoid 1 and 2. There are different ways of cashing out instability. And I think, Dave talked about in his book and you talk about in your papers, there's an extreme version of unstable that consider Boltzmann brains at a time. But also there are moderate versions, Boltzmann bubbles, that have 500 years of history before this moment. And they can do science, normally do, but they'll be wrong about the Big Bang, they'll be wrong about what happened 1,000 years before. But then we write about the science revolution and all the things that have been supporting system mechanics. So that will be stable locally and moderately, but not stable for, say, cosmology and astrophysics. So if we think about this kind of Boltzmann bubble scenarios, then I was wondering, do you think we should also assign zero prior on them, or should we allow moderately higher prior on them as a theorist? And what would be the reasons, principal reasons, to say ban them all, or just like ban the extreme version of them?
So I think that those bubbles, I mean, I do talk about them in my papers. They would certainly exist. You can calculate the probability of individual observers with certain macroscopic information, larger bubbles, et cetera. Usually, when you have a lot of conditions like those bubbles, you also have a lot of individual observers. And I think that the general principle is, if I conditionalize on some set of macroscopic information, that kind of scenario predicts that the rest of the universe is in thermal equilibrium. And they're still cognitively unstable. You might have a fact that you're choosing to look at certain observers who luckily got it right. But they didn't have a good reason to get it right because there's more observers who got it wrong in the same universe.
Location probability, there are objective norms or objective
I
choices.
don't think you're allowed to define your self-locating probabilities to say, I'm one of the people who are correct about the universe.
Well, think about even in a rating case, the Carroll. There are norms about self-locating probabilities. And they are going to be undetermined by evidence too. The self-locating severability principles and so on. You cannot learn those principles from evidence or from macro conditions. So there are norms you endorse anyway.
Sure.
About objective good norms on credence, self-locating credences. Why not allow them here?
Because they invoke inaccessible God's eye information, and there will be most observers who get things wrong with that prescription. I want to do my best to come up with prescriptions so that most observers get things right.
Okay, just one last thing. But every rating case, think about this. Normal without both break, every rating case, many branches. Suppose someone says, so data says, most observers are wrong, or most in the sense of there's other weird measures of most, not Born measure. And you say that's wrong. This is the wrong way of thinking about self-location because you have your own measure, self-locating measure according to the Born rule. So there is something here going on, I feel like intention with what you said about, you're measuring here with some kind of indifference measure over all the observers in the actual universe. But that doesn't come, it's a theoretical thing too. It's not something part of our evidence. What is the right measure of?
It's a theoretical thing, right? So like I said, I'm at peace with the existence of self-locating uncertainties and the need to put measures on them and the fact that those measures can't be deductively reached by looking at evidence. There is something epistemic and normative, et cetera, about them, and that's fine.
And here too.
Absolutely. But you can't cheat by pretending you know where you are in the universe if you don't. In Everett, you don't do that. You say ahead of time, I know the wave function, I know how to spin a branch, I'm going to make predictions. You're not helping yourself to indexical information you don't have.
Okay, Heather.
All right, I'm gonna go in a totally different direction. Can you help me understand more about the locality thing? So in the end, you were saying that there's kind of maybe preferred way of dividing, the states. And so not into like clocks and system, but system and environment. And I was just wondering, through these nice little circles, what's going on there? Like how local is it? And how does this, I know about entanglement. Is this a worry or a consequence? And what's happening?
Well, it's just quantum mechanics. So the idea is that you will eventually go from a list of energy eigenvalues to the standard model of particle physics, to quantum field theory in some background space-time. So the ground state or near ground states of that theory will be highly entangled with each other. This is just by itself a statement about the Hamiltonian, not about the state. So this is about our ability to factorize into subsystems that have direct interactions with their nearest neighbors and no non-local interactions. Generically, you can't do that for a generic spectrum of the Hamiltonian. There's a subtlety that maybe you can come close, and that's work in progress, but generically you can't. So looking for a local factorization when it exists, we'll say this is the right way to divide up Hilbert space so that it looks like fields in spacetime. And then it's just ordinary quantum field theory.
And is this gonna be in like a three-dimensional space or like the Hilbert?
In principle, I mean, the dimensionality of the emergent space depends on the spectrum of the Hamiltonian. And that's given to us by people with higher salaries than me.
But the locality you're
us.
talking about, is it like an effective locality?
It's 100% effective. I feel bad. Alyssa May is editing this volume on locality in Everett, and I wanted to write something for it. She wanted me, I just didn't have time, but it would have been called Stop Worrying About Locality. The universe is not local. We know there's such a thing as gravity. We know that locality is not exact. Don't feel bad. The question you should be asking is not, how do we learn to live with the non-locality of quantum mechanics? The question you should be asking is, why does the world look local at all?
Isaac, and then.
Yeah, I think it's sort of related to some other questions. A way to put this would be, what's special about the problem of how time emerges that doesn't arise for like how I emerge from matrices or wave functions? If you're happy saying, so I'm not happy with the pattern talk. Because it feels, yeah, vague to me, but if you are happy, why wouldn't you be like, oh, time, it's a pattern in the quantum state?
Well, because it seems from what we know right now to be a super highly non-unique pattern. This is the thing that gives us hope in the case of space and fields and things like that. There's some notion that there is a best factorization to give us autonomous higher level dynamics. I can't see how to get that in the case of time, but we're still working on it. But that's the difference.
Shelley.
How widespread is the view among Everettians that you seem to be advocating? Namely, that time is in some sense fully emergent.
I'm not advocating that.
Sounds like.
I am, no, I'm exploring the possibility for the purposes of this
Yeah.
talk.
Yeah,
But I have no idea whether it's true or not. I'm very open about that.
how widespread is that?
The people who are self-described as Everettians in the foundations community, they think about like everyone else in quantum foundations, they think about like a couple of non-relativistic particles moving in the Schrodinger equation, right? So they don't worry about the emergence of time. The working quantum gravity, quantum cosmology people are pretty happy with the Wheeler-DeWitt equation. Oops, sorry, I'm hitting the wrong button. With the Wheeler-DeWitt equation, and that they will cheerfully tell you that time is emergent, but they don't realize that that comes with a lot of problems. And they're also Everettians. So I guess what I'm saying is there's a big group of people who are both Everettian and have this problem. There's a very tiny group of people who realize that they have this problem because they're worried about different things.
Have you discussed your ideas with Thibaut Damour?
No. I thought Thibaut was like working on gravitational waves and testing
No, but
scalar fields and
he's
things.
a very committed Everettian,
Oh, I didn't know that.
and he's very committed to the emergence of time in the most fundamental way. Really,
Okay.
nothing really like time, but you do the analysis and you get this sort of correlation. You should read.
I did not know that. Yeah, no,
Yeah, take a
I'm
look at
happy
his
to be
book.
on the
Take a
team.
look at his book. It's
Yeah.
a very nice book.
What is the book?
What's it called?
Couldn't have written too many. I'll
I don't remember the name, but it's a nice book. You'll like it.
Great.
Oh, could you go to the next slide? I wasn't gonna ask anything, but since Shelley just brought up the problem of time, I thought I'd ask. I forgot about the Page-Wooters thing, and one issue that comes up when you do a kind of emergent time and canonical quantum gravity, like when you like the way Banks does it, or the semi-classical time thing, is that the assumptions you make are only justified in a temporal context. And so I was wondering, because you said that if they make assumptions and you get an effective Schrodinger equation. And so do you think something like that happens here in the Page-Wooters too?
Good. So I should say, and I actually meant to say this when I was planning the talk, when I was teasing philosophers at the end and said not many have thought very carefully about the emergence of time, there are a few who have, and Craig has actually thought about this. So I hope you didn't feel bad. Good for you for not being grumpy at me for that. But, that's a very good question. So what Craig is pointing out is that in the set of people, again, more foundations of physics oriented, if you ask them about the emergence of time, they would point to this Page-Wooters paper as sort of a foundational way of thinking about it. There's a whole nother set of people who are once again, the working quantum gravity, quantum cosmology people who might do some version of work that was done in a paper by Tom Banks in the 1980s, and similar things were done by Carroll and Hawking and others, where they basically, they think that they know what the answer is supposed to be, and they know what the Hamiltonian of the universe is, and they say, let's specialize to some small number of variables, like the scale factor of the universe, or a scalar field or something like that, and they quote unquote use that as a clock. And they derive an equation that is similar to this with respect to the scalar field, et cetera. I have not ever quite been able to reconcile these two approaches. I haven't tried very hard. I suspect that they're morally the same. But I've never sat down and done it. And again, there's the set of people who overlap that way is small, so I don't know if anyone else has done it either.
Barry?
I was thinking about something, but I'm not sure. I mean, at the beginning, you had some questions about that people asking. One of them was what exists,
Yes,
and that's supposed to be the question the philosophers ask.
I think so.
So
I mean, if physicists ask you, they
I
don't
think
get
it's
tenure.
important to distinguish what exists and from what exists fundamentally.
So you're saying even the philosophers don't ask this question?
No, they do, and they make that distinction.
Sure.
And I got very confused in this whole discussion about the various views about what's being claimed of what exists fundamentally and what exists. I mean, a lot of things I know what exists, and well, they might be defeasible in a sense. If somebody were to say, you know what, you think that you were alive yesterday, you really weren't, and here's some, and why would I come to believe that? Well, maybe the theory that I've developed now in order to account for the things I want to account for might have the consequence that I wasn't around yesterday. When I balance those, I think, well, no.
Good.
That's a bad.
I was worried there for a second. Good.
That's a bad theory. Okay, so I mean, see, the way science develops is you start out with the things that we know about the world. You try to make good sense of them, at least the other things that make good sense of them. And then we're off to the races. And you said how far to go. Well, be careful about how far you go when you're at the edge of a cliff. And it looks like that's what's going on here.
So, well, I'm very sympathetic to everything you just said. I think that the cliff has to be faced up to precisely because we don't have consensus about either the foundations of quantum mechanics or quantum gravity. So I think that in lots of circumstances, these kinds of questions you don't need to worry about, and you can shut up and calculate if that's what you want to do. And we all agree on what exists, tables and chairs are real, etc. But here's a set of examples where I think, I think that the failure to quantize gravity and our inability to agree on the foundations of quantum mechanics are related problems. And I think that facing up to some of these issues that might be construed as optional, could ultimately be a way to make progress.
Well, I was agreeing with that, and just don't forget where you started from. And that you wanna make sure whatever, well, I mean, I think it agrees with what you're saying too. But you wanna make sure that any theory of the universe that you come up with, still has where you started from in it.
100% true, but there's literally some kind of cognitive bias, because you know what the universe looks like. And you start to see it in your theory. And I kind of want to be hardcore about, let's imagine I didn't know what the universe looked like. Would my theory really predict that, or am I just fooling myself? I think that's also a legitimate attitude to take. At the end, you want the universe out. You want the real world out. Yes.
Okay, I didn't really figure out clearly what I wanted to.
Okay, I think you did a good job, yeah.
All right, so we're gonna finish there. Thank you very much.
We have a coffee break now till 4:05, so we'll be hopping back on our regular schedule.
Oh, you're not gonna be back.
Thanks for putting up with this.
I think it worked.
Yeah, I thought it was. Thank you.
That was a good call.
Like a couple more cycles of my brain, and I didn't know that. So I did not get that good talk, but I really like it.
I thought it was great. Okay.